A Cyclical Periodic Table by Landon, Josh, Sebastian, and Julian.
When faced with the challenge of creating a representation of the periodic table as a circle, our minds came together to explore how we could somehow create a 3D projection that not only accurately organized the elements, but also detailed the atomic masses of each element. We settled on creating a model of a cyclical table in Fusion that was made of 4 components, each one representing a different subcategory of elements. These 4 components and the elements they hold would then be 3D printed and connected with magnets. The individual elements are labeled with their respective symbol and then extruded to a designated height in order to represent the relative mass. The conversion factor can be illustrated by this equation. To sum this up, the greater the atomic mass, the greater the height of the element in the 3D model.
Attached with the solution, we have every single element as well as the converted extrusion height using the formula. The mechanics of the item. The design is made up of 4 individual pieces that can be connected together via magnets as shown. There is a compartment on each side of a piece that holds a magnet and can form the design if connected together. First section. Alkali metals, alkaline earth metals. The blue section of the circle details groups 1 and 2 of the table. However, hydrogen and helium are separated from the main body to show how, while those elements are both technically in group 1 and 2, their properties are more related to the noble gases and nonmetals.
Alright, now we got the metalloids and the nonmetals. The orange section of the circle shows the metalloids and the nonmetals, and they're commonly grouped together in chemistry, as evident on the normal periodic table and ours. The noble gas row aligns with the helium element in the blue section because, that's what happens on the real periodic table as well. And then now we got the metals. The red section of the table, it just shows the metals. The rows decrease in height as you get closer to the center, and it shows the differences of the weight of each element pretty effectively. I like how that one turned out.
Now for the 4th and final section, otherwise known as lanthanides and actinides. These are the rare earth metals. On the real periodic table, this section is separately located below the metals and alkali earth metals, which actually makes our design better because it much more effectively incorporates these metals into the periodic table, instead of just separating and sectioning these off below the periodic table. Now, as for the purpose and benefit of this version of the periodic table, it's helpful because of the organization of the elements and how simple it is to actually construct. Anyone with access to a 3D printer and the appropriate file can download, print, and have it ready in less than a day. It also helps people whose learning style is more kinesthetic, i.e. doing and feeling opposed to hearing and seeing. And the sections are color-coded to easily distinguish the differences and identify which element belongs to each section. Additionally, the table's height variation helps differentiate the atomic weights from one another.
Alright, and this is our actual project. This is the final, render project of it on Fusion. This is basically, what it is. This is what it would look like if you 3D printed it and you were able to, have all the different parts. Here I am. I'm going to move it up a little bit so you can see, each section is its own section. You'll connect them with the magnets. And it'll be about, if you were to print this out, the diameter would be about 9 inches, which is pretty cool. And I'm zooming in here so you can see, all the element symbols. Those are all engraved into the plastic or the PLA or whatever you're going to print it out on. If you can see, just look at how tall it is. It's only going to be at its highest point about 4 inches tall. And then, like I said, about 9-inch diameter. So yes, that is our project.